Join with computer audio. Okay. All right. I wonder if there's anybody with me here. Nope, nobody. Kind of lonesome, but we'll wait. It's only, well, we got 5 minutes before class. So we'll just patiently wait. What is the topic for today? Well, I think it's just more Newton's second law. I think the topic is Newton's second law. And I think we're still in the XY coordinates. And next time we'll get into the normal tangential components and I guess the other one, what's the other one? Radial transverse components. Hey, I've got somebody, Ashley's here with us. Hello, Ashley.
Good morning.
You're the first one to show up this morning, Ashley.
I see.
Yeah, so you're an important person.
I had a quick question about the exam.
Yes.
Is it okay if we wrote it on the engineering paper and turn it in like that, or would you prefer us to print out this paper from the PDF?
It's okay what you said at first, but I prefer that you do it on the paper that showed up on Blackboard.
Okay.
Yeah, that'd make me happy. But I won't count off or anything if you do it on a different, what would you say, engineering
paper?
That'd be all right.
Okay. Just want to make sure.
Any other questions for me?
I think that was it.
Okay. Good for you. Yeah. When's it due?
It's due tonight.
Ooh, tonight. Yeah, that's right. The 16th, at midnight. Oh, you'll get it done. Hey, look, we got some more students. Nicholas and Ryan are on now. And hello, Nicholas and Ryan.
Good morning.
Good morning.
Hello.
Hello. I just took a walk with my dog. It was cool enough that we both enjoyed our walk. It's going to get hotter.
Pretty nice out there.
Yeah, it's really nice. Let's see. I want to, yeah, there we go. How about any of you? We have 2 minutes before class starts. Did you have a comment or question on anything?
Are we just supposed to email the test to you, or are you gonna make a Dropbox?
There should be a link, and you can submit it just like you do your homework. You're able to submit your homework on that link, aren't you?
Yeah, I didn't notice one.
Yeah, just submit it up with that link. Now, who was I just talking to? Who was that?
Nick,
That was Nick. Okay, Nick. Anything else? Let's see. Let's see who else we got here. No, it's just the three of us, Nicholas, Ryan, and Ashley, for right now. And we're still studying the most important equation in the course, Newton's second law. And in XY coordinates, it amounts to this. There's Newton's second law, and you can do it in the X direction or in the Y direction. Now, it's one thing to know Newton's second law, but it's something else to be able to actually use it. There's an art to being able to use a tool, as you know.
I know, but
Hey, look here, we got Braxton. Braxton's with, and Shane. We got a good class here. Braxton and Shane, somebody else, but I can't seem to find them there. Okay, here's your last chance to ask me anything. All right, well, let's just launch into some examples. I think the best way to do this is just to work problems. That's the theory. There's no use spending a lot of time on that theory. That's it. Now, if you have 3 dimensions, you could have a z. You could have a sum of the forces in the z direction. That'd be okay. It's kind of a funny z here. I'm no good at drawing z's. Let's just put a z like that. How's that? There we go. But hey, let's just learn how to do this stuff in 2 dimensions for right now. So we don't even need that last one. Was there any particular problem that you wanted me to work, or do I get to do what I want? Because if nobody has a request, I'm just going to launch into the things that interest me. Okay, well, why don't we try, see, we're going to start next time on the normal tangential. So this is our last time specifically on the XY stuff. Never mind the Z stuff, we're not going to do that. Let's do some of these review problems. This is sort of a review problem 13.4. Let's do that. It's on page 176. Okay, now let me find it here. What I like about these problems in the book is if they have answers, you can go to the back of the book and check the answer, and if you get the answer they got, it makes you feel good. Makes you feel like, hey, maybe I'm learning this stuff after all. Okay, now this is R13.4. There's a crate here on a level surface. And it's connected to a motor. Okay, let me read this now. It says, the motor draws in the cable at a rate of V equals 0.05 0.05 s, say the 3/2. Now that'll be in meters per second. Okay, and now they're talking about the crate going to the right there with a velocity. This equation gives the velocity of the crate, and it depends on this distance s. Now this distance s is some distance from probably a y-axis. You could call this the x-axis. And s is the distance from that y-axis. Now, did I get all the info? Let me read this. Oh, mu sub k is 0.2. Let me write that down. Mu sub k is 0.2. I get all the information. Wait a minute. It's a 20 kilogram. Let me write that down. 20 kilogram. Okay. And they want to know the tension when S is 10 feet. So see, there's tension in this cable. Now you know how to do these problems. You get your red pencil or pen, and you put all the forces on it. Now there's going to be a gravitational force that's going to be, I think it's 196 newtons. 196 newtons. But let me double check that. I don't want to mess up here. Take 20 times 9.81. I came close. It's 196.2. 196.2 newtons. And then you'll have a normal force. That normal force in this case is 196.2 newtons because it's not accelerating in the y direction at all, so the forces have to be equal and opposite. Then you have a frictional force, and you have a tension. That's it, guys. There's 4 forces on that block. And that's supposed to be an arrow. And there's friction pushing on it. I don't think it's that big, though. See, the way friction works is friction is 0.2 times the normal. Well, we have the normal, so we can get the friction. Here goes. Take 196.2 times 0.2. I'm getting 39.24. So we know the friction. Let's circle it. We know the friction. We know these. We got the numbers. I think they want the tension. Now, to find the tension, we'll have to use this. Newton's second law. But it has acceleration. We don't have acceleration. We have velocity. So to get acceleration, we're going to take the derivative. You know how to do that. The acceleration is the derivative of the velocity. So you're going to take the derivative of this velocity while I shut up for about a minute. I mean, I'll give you a minute and a half if you need it. I want you to take the derivative of the velocity with respect to time, not s. S is a distance. So acceleration is derivative with respect to time. Now go ahead and do that. And then we'll share what we came up with. Go for it. I'll be quiet. Find the acceleration. That's what we're doing right now. Go. Well, I wonder if that's enough time. Let me find one of my very best, brightest students here. Jackson, you're on my list here. Jackson, unmute and say hi, please.
Hey.
Yeah. Jackson, have you taken this derivative of this velocity to get the acceleration? Have you done that?
I'm still working on it.
Yeah, that's okay. Work away. We can wait. The others are probably working on it too. Now, Jackson, don't forget the chain rule, Jackson, the chain rule. Have you ever heard of it? Jackson, what do you have so far? Go for it. We need this acceleration. What'd you get, Jackson? Earth calling Jackson.
Yeah.
What do you have so far, Jackson? Are you just stuck? Is that the problem?
Yeah, it just nothing.
Talk to me. What do you got so far, Jackson? I know you got something. Tell me what you got. What do you have so far?
I'm not sure.
This is your lucky day. We're going to show you how to do this. The thing is, you already know how to do this. You know how to take derivatives. Just maybe when you call on people, their mind goes blank. All right, here's what you got to do. You have to take the 0.05, of course. It's just sitting in front. We don't throw it away. And then you take the 3/2 and you multiply by 3/2. And then, Jackson, what do I do now? I'm going to have s to a power. What's that power going to be, Jackson?
1/2.
Yeah, good going. Good going. See, he knows how to do this. But see, you're not through yet because we're not taking dv ds. We're taking dv dt. So you have to use the chain rule. So what goes right here, Jackson? You have to use a chain rule.
WS.
Yeah. Say that again.
WS3/2 after that.
Say it one more time. I didn't quite hear you.
WS3/2 after that, right?
WS? Did you say WS?
No, just S.
Just
2.
DS? I still can't hear you. Say it one more time.
S3/2.
I'm sorry, I can't understand you, but I know what I want. I want DSDT. Is that what you're trying to tell me? Is that what you were saying? Because that's what it is, see?
Yeah.
It's DSDT. Well, as long as I got Jackson on there, Jackson, DSDT is equal to something that we know and love. It's a beloved quantity. It's the derivative of position with respect to time. And that's equal to what, Jackson?
The velocity.
Yes, good going. See, you understand this stuff. And we already have the velocity, so let's plug it in. Here we go. We're going to plug it in. Now let's see, we have all this stuff. Let me write this down now. We have 0.05, 3/2, s to the 1/2 times v, which is 0.05, s to the 3/2. Okay, and now what we're going to do is just clean that up a little bit. I won't pick on you for a while, Jackson. You're off the hook for a few minutes now. But we're gonna multiply the numbers, and we're gonna combine these s's here. And I'm gonna do that, and I want you to do it. And then I'll call on one of my other wonderful students here. So go ahead and clean that up and make it pretty for me. Go ahead. Okay, make it pretty. Let me go to one of my wonderful students here. Hey, Braxton, unmute, and say hi.
Hello.
Hello, Braxton. When you clean this up and make it pretty, what do you get?
0.00375 s squared.
That's exactly what I got. 0.00375 s squared. Yeah, good going. Hey, we got the acceleration now. We're coming on. And what is s? Well, they said they want s to be 10, remember? Okay. Well, if it's 10 and 10 squared is 100, I think we just figured out what the acceleration is. It's 0.375 meters a second squared. Because see, if you take 100 times that, you move it over 2 places. We're coming right along. We don't need this equation, but we're going to use this equation now. Now look at here. We know this. We just figured it out. It's 0.375. And we know this. It's 20 kilograms. Now we're going to write our Newton's second law in the x direction. Here goes. We have t going in the x direction to the right, minus the friction, which is 39.24 newtons. And that's it. That's it in the x. And that's equal to the mass, 20 kilograms times 0.375 meters a second squared. Now we're going to plug that in and we're going to get the tension. Now do that, and I'll call on another wonderful student here in just a minute, and we're going to get the tension. Go for it. Find the tension. Okay, I'm gonna find one of my wonderful students here. Ashley, you were the first one to show up for class today. You have the honor of telling me what the tension is. Do you have it yet?
46.74 newtons.
Okay, I must have done something wrong. I didn't get that. Let me do it again. You're probably right, Ashley. Ashley is right. Whatever I had, I don't know what I did. I did something wrong. I think that's what you just said. Now wait a minute. Ashley, what's the units that go with this tension?
Newtons?
Yeah, newtons. Good going. Now let's check and see how we did. This was problem review. R stands for review. It was review problem 13.4 is what we just did. If you tuned in late, we're kind of going over some basics here about Newton's second law. Now go to the back and let's see what they said. They have answers for these review problems. And for this one, 13R 13.4, it's on page 725. If you look on page 725, they have the answers. And they said 46.7, the book says 46.7 newtons is the answer. And I'm pretty happy with ours. We got 46.74. They just rounded off. We did great. Now, does anybody have any problem with that? Any question with review problem 13.4? Anyone? Okay, well, if you're happy with it, I'm happy with it. Let's do another problem. Here's your chance. If you didn't understand something, speak up. All right, I'm going to erase all this, and we're going to do a different problem now. See, we're studying Newton's second law. This says the sum of the forces in the X. Well, there was two. There was the tension, and there was the friction. See, we have the tension, and we have the friction, and it's equal to the mass times acceleration. Okay. All right, well, if you're happy, let's go on. We're studying Newton's second law. Okay, now let's do this one. This is a review problem 13.2. We just did a review problem. This looks a little harder, actually. It's on the same page. It's on page 176. And you know the drill. You know you're supposed to draw the free body diagram. You're supposed to draw the diagram of the body there. There's a crate. It's on a 30-degree hill. You know, I can even get the angle here. See, that's what you're supposed to do. You're supposed to actually measure this stuff. All right, I'm going to measure it. I've got a protractor. I can measure 30 degrees. Okay, 30 degrees. Let's see. All right, 30 degrees goes right here. There's 30 degrees right there. All right. We have measured this. Do you do that when you do your work? Do you measure stuff? You're supposed to. So we got 30 degrees, and we have a crate here. I'll draw the crate for you. There you go. And it is, do we know the mass of this crate? Let me read this. It says, yeah, 50, it's a 50 kilogram crate. You know, that's over 100 pounds. 50 kilograms. I wonder what's in it. Gee, the 100 pounds, the crate itself looks like it could weigh close to 100 pounds. Okay, and then you've got pulley system. We're going to have to think about this pulley system. And it's connected to a motor. There we go. Well, where does this go? This just goes to a wall someplace, and it's attached. We got the motor here. They call that M. They have a point P for some reason right here, and a 30-degree angle there. Okay, we got all that. Let me read this, see if I'm forgetting anything. It says the motor pulls the attached rope with an acceleration of 6 meters per second squared. You see this point P right here? I tell you what, take some color, like maybe, I got some blue here. And put a little blue paint right there. You see that blue, that splotch of blue paint? It's got an acceleration into the motor of 6 meters per second squared. The acceleration of that point P is 6 meters per second squared. And it's winding up. It's going into the motor. But we need the relative motion equation. Now notice there's 3 ropes pulling on your crate. See that there's tension in this rope, there's tension in that rope, and there's tension in that rope. There's 3 tensions on the crate, but only 1 tension from the motor. So the way you write that equation is you go 3 times the velocity of the crate. They didn't give it a name. We'll just call it crate. Is that how you spell crate? C-R-A-T-E. 3 times the velocity of the crate. And here's where I'm getting confused. They're both going up the hill. So you would have to be a negative velocity of the point P equals to 0. I mean, they're not going in opposite directions like we usually, when we write our dependent motion equations, where you have something going down and something going up. These are both going up. And can you see that the velocity of 3 times the velocity of the crate will equal 1 times the velocity of the blue paint marking on your rope. They're both going in the same direction. We're not going to get confused about that. They can't go in opposite directions. And so if this is 6, the velocity of the crate would be how much? Well, it would be, oh, wait a minute. No, that's not velocity. Hang on a minute. Let's take the derivative before we do anything else. If you take the derivative, then you have the acceleration of the crate minus the acceleration of your point P equals 0. Now, if the acceleration of point P is 6, then the acceleration of your crate is 2 meters per second squared. Did I lose anybody on that? See, we're going to use Newton's law. And look here, we just found the acceleration and we know the mass. Ooh, we're doing so good. We have the right-hand side of Newton's law just fine. Now we have to do the left-hand side. Now this is the sum of all the forces. I like to get a red color to do that. Can you see that this tension is pulling? There's a tension pulling. And this rope here, that kilogram sign kind of got in my way. But there's a rope here that's pulling on the crate. And it's 2T because you have 2 ropes pulling on it. See this, there's T here, T there, T there. You got 2 ropes. So what we have going up the hill is 3T. So here goes Newton's second law. We have 3T going up the hill minus, and don't forget the friction. There's friction here, I think, isn't there? Let me read this again. Yeah, the mu sub k is 0.3. We've got a mu sub k. That's called the coefficient of kinetic friction. And so the friction will be mu sub k times the normal. And in this case here, we've got to find the normal. Well, there's a weight here of 50 times 9.81. Let me get that. 50 times 9.81. I'm getting a weight of 490.5 newtons. See, that's the weight. That's the weight. Now the normal is here. And so to find the normal, you have to write the sum of the forces in the y direction. But see, the sum of the forces in the y direction, well, it's equal to ma2. It's just that a is 0. It doesn't accelerate in the y direction. All the acceleration is in the x direction. Here's the x direction. Here's the y direction. And it does not accelerate in the y. So we just write the sum of the forces in the y. And we have this normal. It's in the y. And we have a component. See, this tension has a component. It has a component going down the hill and has a component going perpendicular to the hill. That component is the weight, which is 490.5 newtons cosine of 30 equals 0, so we can get the normal. And once we get the normal, we can find the friction. Now I'm going to shut up for about a minute and a half, and we need that friction. So go ahead, find that friction for me. First find the normal, then multiply by 0.3. Get the friction, go. Well, I got the friction, and let me see if anybody out there can help me. Alex, Earth calling Alex. Unmute and say hi, Alex.
Hello.
Hello. Alex, did you get the friction yet?
Yeah.
What'd you get?
127.43.
That's what I got. We think the friction is 127.43 newtons. Good going, Alex. Now we're going to write Newton's second law. Now we got 3 T's pulling it up the hill. We have the 127.43 newtons of friction that's trying to push down the hill. But there's one other force. There's actually 3 forces in the x direction. The 3T is in the x direction. The friction's in the x direction. But see, there's a component. There's a component of this weight pulling down the hill. And so that's going down the hill. That's negative 490.5 newtons times, it would be the sine of 30. Or the cosine of 60. You get the same thing. If you prefer, you can go cosine of 60. And this, oh gee, I ran out of room here. But this is going to equal to the mass, which is 50. Uh-oh, ran out of room times A. Can I squeeze that A in there? Yeah, maybe. The thing is, we got the A someplace. Oh, there it is. It's 2. Now look here. We have an equation. And we know everything in this equation. We know A, I could circle it here if I had room. It's 2. And we can solve for the tension. Go ahead, I'm going to shut up for a minute. And I want you guys to solve for the tension. And I'm going to solve for the tension. Go. Well, I solved for the tension. See that's the tension in the rope connected to the motor. That's what they want, isn't it? Yeah, that's what they want. They want the towing force exerted by the motor on the rope. Well, that's the tension in the rope going into the motor. And I got it. And let me go to my my student here. Let's go to Stuart. Stuart, you're a good sport. Unmute and say hi.
Hello.
Hello. Stuart, did you get that tension yet?
Yes, I got 157.56 newtons.
That's what I got. It's exactly what I got. Well, we solved the problem. Let's see how we did. Now, in the back, they have answers to the review problems. We're kind of doing a review here. We just did review problem 13.2. It's on page 176. We're trying to know how to use Newton's second law. Okay, let's see what they said. 13.2, answer book says tension is 158. They just round it off. The book says the tension is 158. I think we did great. Anybody have a problem or want to make a comment on problem or review problem 13.2? Here's your chance. Well, we're doing great. We got a couple of problems under our belt there. Let's do some more pulleys. See, this involved pulleys, didn't it? Let's do another pulley problem. Let me make some room here. I'm going to erase this if it's okay. So you guys are okay with this. Newton's second law. See, you have to include all the forces. There were there was a tension here and two tensions there. That makes three tensions. There was a friction going this way. And then the weight had a component going down the hill. You don't want to forget anything. You forget just one force and it's over. You're not going to get the right answer. Okay, we're going to do another problem. Now this one doesn't have a, I don't think this one's in your book. This is just a problem that I give my students. It's a pulley problem. Okay, we've got ourselves a pulley problem. Now C here is 2 kilograms. B is 3 kilograms. And A is 6 kilograms. And what we want to do, we want to find the tensions in all of these connections here. There's a rope here or a cable or a cord. We want to find the tension in it. And there's a different cord here, see it? We want to find the tension in that. And this here, this could be a rope or it could be a strap or a piece of metal. We want to find the tension in it. But the first thing you have to do is to write the dependent motion equation. Write the dependent motion equation. Now, if you get this wrong, you're never going to get those tensions right. You'll never get them right. So I am going to shut up now for a minute. At least a minute, because you might have to think about it a little bit. And I want you to write the dependent motion equation. I've shown you how to do it. In fact, I've shown you a couple of ways to do it. Go for it. See if you can write the dependent motion equation. Well, some of you might be done by now. Let me call on my student, Shane. Shane, unmute and say hi. Shane.
How you doing?
Hey, doing great, thank you. Shane, have you written the dependent motion equation yet?
Believe so.
Yeah, what'd you put?
The velocity A plus the velocity of B plus the velocity at C equals 0.
Shane, you are truly blessed because you're going to learn how to do it right today. That's not right.
Okay.
Now let's call on somebody else. Now, if they get this right, then they aren't truly blessed because they already know it. See, Shane's going to learn how to do this. Let me ask somebody else here. How about Mark? Mark, unmute, Mark, and say hello. We'll put an unhappy face on this one. This is not right. Mark, say hello. Hello, Mark. Come in, Mark.
Hello.
Coffee break. Let's find my friend Ryan. Ryan, unmute and say hi.
Hello.
Hello. Ryan, did you try the dependent motion equation? See, we got an unhappy face on this one. What do you have one?
I have 2 VA plus VB plus VC equals 0.
Okay, now let me think and see if that's right. Let me think and think and think. You know what? I think Ryan's, we'll put a happy face on that one. I think Ryan's right. And now I showed you a couple of ways to do it, but the easiest way is you just put a tension here, around here, put a tension there. And if you have 2 tensions pulling down, that means there's 2 tensions in this rope. Going around here, you have 2 tensions. And so Ryan did great. You've got 2 tensions on A, but only 1 tension on B and only 1 tension on C. That's it. This is the correct dependent motion equation. Now, what we really need, though, is to take the derivative of that. And you know the derivative of velocity is the acceleration. So now we're going to write the dependent motion equation for acceleration. Ta-da, we just did it. Okay, now the next step. The next step is we need to get our red pencil out and we need to put our forces on here. Now this one here is going to have a 19.62 newtons and a tension going up, but I don't know what the tension is. Now this one's going to have just a minute. I don't know what 3 times 9.81 is, but my calculator does. 3 times 9.81. 20. This one's 29.43 newtons going down, and you have tension going up. And this one has, well, wait a minute, 6 times 9.81. Man, that's going to be big. 58.86. This has got a humongous tension of 58.86 newtons going down. But now the tension is 2T, so I need to draw that a little longer. I don't know, maybe like that. It's 2T. But again, I don't know what T is. And I don't know what 2T is. But this is how you do problems. You write the dependent motion equation, You draw your situation, your free body diagrams, and then you get your red pencil out and you put all the forces on your bodies, and we did that. And now the next step is to write Newton's second law. Okay, well, let's do that. I need a little room here to do that. Okay, we're going to write Newton's second law now. And we'll write it for each body. Now, here, when you do this, you have to decide which way is the positive direction. Let's just write all of our equations. Positive direction going down. You could do it the other way. You could have all of them. But whatever you do, you have to make up your mind. And if you're going to go down, then stick with it. Okay. Now, the sum of the forces on A will be going down. We got 58.86 going down minus 2t equals acceleration of A. Wait a minute, the mass of A, 6 kilograms times the acceleration of A. Then I just wrote the Newton's second law for body A. Okay, now let's do Newton's second law for body B. That's going to be 29.43 minus just 1t equals 3 acceleration of body B. That's the Newton's second law for body B. There's only 2 forces on it. Now for body C, we have 19.62 newtons minus just 1t equals the 2 kilograms times acceleration of C. Okay, now let's look at what we got. We have 4 equations. See here, I'll box them up for you. There's this one here. Well, there's 3 of them there. And this one here. We have 4 equations. We have 4 equations. And we have 4 unknowns. The unknowns are t. We don't know t. We don't know the accelerations. There's the 4 unknowns. We have 4 equations. We have 4 unknowns. We took algebra in school when we were younger and better looking. We can do it. We can do it. Now, one way to do it is with matrices or linear algebra. But you don't have to go with that fancy stuff. Let me show you the best way to do it, I think. But you're free to use your fancy calculators that solve 4 equations and 4 unknowns. You can do that if you want. But here's the way I would do it. I would solve this equation for the acceleration of A. Just divide by 6. Now, when you divide that by 6, what you'll get is 9.81 minus 0.333, a bunch of 3s, t. Can you get from here to here? Can you make it? Maybe you better double check me there. Make sure I did that right. If I did, I'm going to do this one here now. I'm going to solve for B, acceleration of B. Just divide everything through by 3. It turns out you'll get 9.81 minus Well, I think it's a bunch of threes again, isn't it? Yeah, I think so. Okay. That looks pretty good. Now let's find the equation for the acceleration of c. Here we go. Divide that by 2. I think you get that 9.81 again, minus 0.5t. Double check me on that while I take a sip of water here. And then what we're going to do is we're going to plug them into here. This is a velocity equation. We're not going to use it. We're going to use this acceleration equation. Now, if I made a mistake, you sing out and tell us. It'll help the whole class. But I think I did that right. And now I'm just going to plug them in. Here goes. Well, I'm going to have 2 of accelerations of A. So I'm going to go 2 times 9.81 minus 0.333, a bunch of threes, t, plus 1 of these b's, plus the 9.81 minus 0.3333t, plus 1 of these AC's, 9.81 minus 0.5t equals 0. Looky here, we have an equation with 1 unknown. But if you want to do it with your linear algebra or with your 4 equations and 4 unknowns matrices, go ahead. Okay, now I'm going to shut up for 2 minutes and I want you to plug all this stuff in. And I want you to find the t. I'm going to do it. I want you to do it. On your mark, get set, go. Well, I got an answer. I wonder, let me ask somebody here. I think I picked on most everybody, but I don't know about Nicholas. Hey, Nick, unmute and say hi.
Hey.
Hey, Nick, did you plug that all in and get the tension yet?
Yeah, I got 26.16.
That's what I got. I got 26.16. newtons. We got it using Newton's second law. Now here comes the last step. Remember, this is a step-by-step thing. Here, I'll make you a little list. First thing you do is you make a sketch and you label it and you draw all the pulleys or whatever it is, the bodies, and you do it to scale or measure your angles, and then you put your red stuff in there for external forces. That's the first thing you do. And then what's the next thing you do? Well, maybe the next thing is you put all your forces in red. I guess that's part of the deal. That's terribly important not to forget any. I put them in red so I won't forget any. Put all your forces in red so they'll jump out at you and you won't forget any. Then what do? Well, then you write your Newton's second law equations, right? Isn't that what we did? Yeah, we made our sketch, we put our red stuff in there, and we got our, wait a minute, I'm screwing up here. The first step is the sketch. Well, what about the dependent motion equation? Here, step 0. Step 0 is your sketch. And include all the symbols, tensions and all that. And then step 1 is your dependent motion equation. Step 2, put all your forces on there in red. Step 3, you write your Newton's second law. Step 4, you do some math. That's what my friend Nicholas did. He got the 26.16. And now step 5, this is important too. This is called checking your work. See, we've been checking our work by looking in the answer book. But there's no answer book answer to this because I just made up this problem. But see, there's a step-by-step process here. But we've done all the steps, but we haven't checked our work. And you can't check it with an answer book. But I tell you what you can do, you can check it with common sense. So let's write what these tensions are. We think the tension here is 26.16. 26.16. We think the tension here is 26.16. And this tension here is twice that. I don't know if I can do that in my head. 52.32, it's kind of dangerous. 53.32 newtons. When you double that, do you get 53 point? I don't think so. No, it's 52. Let me do it on the calculator. I don't trust my ability to multiply by 2. 52.32, there we go. Now here's how we can check this. If you got 58 something newtons going down and 52 newtons going up, what's this thing going to do? Well, I would think it would go down, don't you? Because it's got more force going down, right? 58's bigger than 52, so A is going to go down. All right, well, let's see what A is. The acceleration of A, according to this, is 9.81 minus 0.3333 t, and we think we know t. It's 26. I'm going to plug in 26 and see what I get for A. Here goes. 9.81 minus 0.3333 times 26.16. I'm getting 1.09, and it came out plus. What does that mean? Well, it's going down. Plus is down, remember? Plus is down. So that kind of made sense. Now let's look at B. Now B's got 2943 going down, and the tension is 2616. You know what? 26 is smaller than 29. I think B is going to go down too, don't you? Yeah, you got more force going down. You know, A and B are both going down. Let's find what B is. Here we go. Ooh, looky here. Those are the same numbers. You know what you're going to get here for the acceleration of B? 1.09 going down. Hey, you know what? A and B go down together. Neither one of them gets going faster than the other. They kind of go down like a pair, like two birds in flight. You ever watch birds? They'll fly along, and one doesn't get ahead of the other one. They just stay in formation. A and B are coming down, and they're going 1.09. If I had room, I would write meters per second squared, but I ran out of room. Now let's look at C. Now C's got 19.62 going down. Ooh, but it's got 26 something going up. 26 is bigger than 19. See, what we're doing right now is we're checking our work. Common sense says 26 is bigger than 19. C should go up. Zoom, it goes up. Well, let's see what it is. Acceleration of C is 9.81 minus 0.5 times 26.16. I'm getting an answer for C of negative 3.27. Those are meters per second squared. You know, if down is plus, then negative is up. C takes off. It's going 3 times. Look, 3 times. C is going to go 3 times as fast as these. These two go down in formation, and C goes whoosh. It really takes off. Well, it kind of makes sense. Look, if you have a 6 kilogram and a 3 kilogram going down, won't this 2 kilogram take off and go up? We just checked it. This is the method of doing these problems. You make your sketch of your bodies. You do your dependent motion equation, put all the forces in there, write your Newton's second law equations, get your calculator out and solve it, and then check it. Any question on this pulley problem, what we just did? Okay, well, I'm going to erase it. If you're happy, I'm going to erase it. All right, let's erase that one. That was fun. We want to learn how to apply Newton's second law. Let's do one more. Now, I don't have much time, is the sad thing. We only have about 12 minutes, but we could get something done on it. And here's what I had in mind. I've got a different pulley system. A, B, and C. let's say A is 1 kilogram, B is 3 kilograms, and C is 2 kilograms. Okay, we're going to go through our method of doing these problems. I drew the sketch of the bodies, and I'm going to put some red stuff on there in a minute. But before I do anything else, I'm going to get the dependent motion equation. And I'm going to shut up. And I want to see if you can get the dependent motion equation. I'll give you 1 minute. On your mark. And get set, go. Write the dependent motion equation. Now let me remind you that you do have some homework. It's problem 1323, and it's due, I think, Saturday night. So you do have homework. Yeah, that's homework assignment number 9, I think. You also have homework that's due tomorrow night. Here, let me write this down. It's all on the syllabus. This is tomorrow night, and that's 13.3, I believe. This should be on your blackboard. And then this is due the 19th, which I believe is that's Saturday, isn't it? I don't know. Let me look. I got a September calendar. Yeah, it's Saturday. And it's 1323. This is homework number 8. This is homework number 9. Don't forget, you have homework. In addition to your test, you got your test. We were going to have it, but I fouled up. And for some reason, the link didn't work, but it's working now. And you guys are going to do that test, and I think it's due tonight. Isn't it? It's due tonight. Okay, so don't forget your homework. Now, let's write the dependent motion equation. We may not have time to do this complete problem, but we can do what we can. I think it's going to look like this by the time you get your acceleration equation. That's it. See, there's one rope attached to C. There's one tension pulling on it, but there's 2 tensions pulling on B and 1 tension on A. So there's your dependent motion equation. And then the next step is to write the Newton's second law. Wait a minute, I forgot to put the the red arrows on there. I don't have time to actually do this problem, but this one will be 2t, t, t, and these will be weights. Put your red arrows on there. And then you write your Newton's second law equations and you can solve it. For those of you that want to practice that, I'll tell you what the answer is and you can do this at home. It turns out that the tension is equal to 14.715 newtons. You can finish that yourself, those of you that are really sincere about mastering this Newton's second law. Go ahead and finish that. You can do it. Just write your Newton's second law equations. We showed you how to solve it. But I have 4 minutes and I wanted to show you something interesting. And then it's sad, but our time together will come to an end. Take any one of these pulleys, like take this one for instance. And we're just going to isolate this pulley and we're going to look at it. And we're just going to kind of take a picture of it. There it is. We're looking at it. And see, you've got tension going up, tension going up. And I've been telling you guys that means that you have to have two tensions going down. See, if these are going up, that has to be two tensions. Well, now well, that may seem obvious to you, but here's the reason why. Right now, we're studying massless pulleys. Massless. Now, the truth of the matter is, there's no such thing as a massless pulley, okay? I'm lying to you. Even if it's light plastic, it weighs something. And so there'll be another force on here. It'll be a force of gravity because this pulley does have mass and it'll have an mg force going down. It's not just these three forces. There's four forces on that pulley. But if it's massless, then you write your Newton's second law. Here we go. The sum of the forces is equal to ma. Well, you've got two t's going up. Well, it kind of depends. If you want to have down be positive, you have two t's going down. And you have, well, you have t going up and t going up. Now, the acceleration is not zero. This pulley is going to have the acceleration of b. I don't know what that is. But the mass is zero. It doesn't matter what the acceleration of b is. So b and this pulley are connected. Whatever b does, the pulley does. But if the mass is zero, then you have 2t minus t is zero. So guess what? What if you didn't know what this was? And you just put in the force there. There you go. That force has to be 2t because the sum of the forces on these massless pulleys is zero. It's always ma, but if the mass is zero on a massless pulley, then the sum of the forces is zero. You're kind of back to statics when it comes to massless pulleys. We've been assuming that all along, but I wanted you to know the reason why. You can just go t here, t there, that makes that 2t. Same here. See, there's a t pulling down here. There's a t pulling down here. There's got to be a force. If that's a rope, it's a tension. Of course, if it's a piece of metal, it's still tension. That's going to have to be 2t going up because the acceleration of that pulley is 0. It's not going anyplace. Well, no, wait a minute. I'm getting mixed up. The acceleration is 0 and the mass is 0. So you got 2 zeros on that one there. And here the acceleration is 0 and the mass is 0. I think you understand. Okay, well, we've had fun and the time is up. Is any last comments or words? It's up to you. Anybody have anything to say? You got your work to do. Get that test, do good. Anyone? Okay, well, I'm going to say goodbye for now. And I will see you, what's that today, Wednesday? I will see you Monday. And I'll get those tests graded. See you then. Bye-bye. Yeah, there's somebody else say bye-bye. Are you still there? Have I lost everybody?
Bye.
Bye-bye. So long, students. See you next time.